Okay, here we go. I've got a note saying start here on Thursday, so I guess that's what we'll do. We did spend Tuesday talking about confidence intervals, right? Building a confidence interval, interpreting a confidence interval. Because we're about to do one again, I'm not going to review it. We'll just kind of review it as it comes up. Okay. But we also introduced hypothesis testing or the hypothesis testing framework. Okay? The hypothesis testing framework can feel quite elaborate in the beginning. And so we're just going to introduce the rules and then we'll go back over and kind of fill in some gaps as we go. But the general framework is this. We start with some null hypothesis, which we're going to denote by H subscript 0, which we read as H naught. And so naught is null, so H null or H, what's a word I shouldn't put? H naught? N-A-U-G-H-T or N-O-U? I don't know. I'll do an A that looks like an O, how about? And it just means 0, right? Null, not, 0, they all mean the same thing. Okay? And so H naught represents the status quo or 0 change, right? 0 difference, 0 change, everything is the same, right? Or, so status quo or equal to, right? Everything is just the same. We also have usually some hypothesis about what's actually going on. Okay? And usually how we denote that is through this alternative hypothesis. Okay? And so the alternative hypothesis we denote with an H subscript A for alternative. Okay? And depending on if you've done stats in biology, for example, they like to use H0, H1, right? And so you can use H or H1 if you prefer, but I like to use A just because it kind of bumps you in the direction of the alternative hypothesis. And so usually the alternative hypothesis represents our research question, right? The thing that we're testing for or the thing that we suspect. So what we suspect, usually. I'll add in usually here. It's not always the case, but usually. And so often what you want to do is you suspect that you have this alternative hypothesis, but what you need to do before you can say, okay, yeah, I've found evidence and my alternative hypothesis feels reasonable, right? What you need to do is you need to say, okay, well, let's assume that my alternative hypothesis is wrong, right? And then you do all your testing and do your math, right? Do your stats. And then you find that the probability that the null hypothesis is true is very small, right? And then that gives you evidence in favor of the alternative hypothesis, right? And so, and we're just building this up. And so don't worry, but just absorb it for now. So we're going to have two competing claims, okay? The null hypothesis and the alternative hypothesis. Now, a hypothesis test is a formal testing framework that we use in all of science. As soon as you want to prove something, science, business, anything, it's the reason you have to take this course, right? As soon as you want to prove something, you need hypothesis testing. And so we conduct a hypothesis test under the assumption that the null hypothesis is true. And we're not going to use simulation. Not in this course. It is an option. Oops. Not in this course, we don't. We're just going to use the traditional methods based on the central limit theorem, which should sound familiar at this point, right? What does the central limit theorem say? It says that we can assume a normal distribution as long as some conditions are satisfied, right? Independence and normality. So that's neat. But the key thing is that we have to assume that the null hypothesis is true throughout all our testing. And so then, if the test results suggest that the data do not provide convincing evidence for the alternative hypothesis, then we stick with the null hypothesis, or kind of more reasonably, right? If the data says, hey, the probability of this being true, if the null hypothesis is true, is very, very small. So then we say, well, if the probability of the null hypothesis being true is small, then it's more likely that the alternative is true, right? We still can't say for certain, right? But if the data suggests that the null hypothesis is unlikely, right, then we reject the null hypothesis in favor of the alternative hypothesis. And there's a very ill-timed typo here, but we'll formally introduce the hypothesis testing framework using an example on testing a claim about a population proportion. One of the ways that we can test the hypothesis is using a confidence interval. Okay, that's nice because we already spent some time and we're kind of familiar with confidence intervals now, or at least we've seen one or two. And so earlier, we calculated a 95% confidence interval for the proportion of American Facebook users who think Facebook categorizes their interests accurately as, and she's really gone ahead and rounded 64 to 67%. Right? And so we said we're 95% confident that the interval from 64% to 67% captures the true proportion of American Facebook users who think Facebook categorizes their interests accurately. Longest run-on sentence there ever was. So we've got an idea of where the population proportion is, right? We're 95% confident that it's somewhere between 64 and 67, right, as a percentage, or 0.64 and 0.67 if you prefer. So based on this confidence interval, do the data support the hypothesis that, I'll say a majority of American Facebook users think Facebook categorizes their interests accurately? Now, whenever you have something like, do the data support or is there evidence? That's going to be your clue. Also, probably that the question's out of 7 marks usually. That's a clue that you need to do a full hypothesis test. Okay? But so is there evidence or do the data support? Those are kind of leading words telling you to do a hypothesis test. So our hypothesis test, we have to set up our null and alternative hypotheses. Yeah? And so hypotheses have to be about the parameter. Yeah? So they have to be about the population. As we mentioned last day, we know everything there is to know about the sample, right? You can calculate p hat, you can calculate the standard error. Those are all things that we can know already. Okay? And so hypotheses must be about the parameter. In this case, it has to be about P, right? The population proportion. The population proportion of American Facebook users who think Facebook categorizes their interests accurately. Now, when we talk about a majority, and you're going to see a majority in a lot of the questions, it's kind of a go-to question, right? Is there evidence of a majority here, right? And so when you see a majority, that's 50% or more, right? So we suspect, right, 64 to 67 feels like it's 50% or more, right? That entire interval is above 50%, right? And so I have a pretty good idea, but how we need to go about it is to say, okay, P, let's just assume P is 50%, right? And so then we say, okay, the population proportion is 50%. I suspect that it's actually more than 50%, right? P is greater than 0.5, but that doesn't show up until my alternative hypothesis. So in order to be able to show that P is larger than 0.5, the first step is to assume that it is 0.5, right? So we jump in and we say, hey, let's assume it's 0.5. Okay? Then if we find evidence against that, right, we say, well, how would I find an interval between 64 and 67 if it's actually supposed to be centered on 50? It's very unlikely, right? And so what we say is, so here, this is what we want to prove. It's got that annoying wobble. Better, maybe? But we first have to assume that P is 0.5 or 50%. To use a confidence interval to test a hypothesis, what we do is we say, okay, if the null value, now the null value is that P is 0.5 or 50%, right? And so the null value is P is 0.50. If the null value is not included in the interval, right, I'm 95% confident that that is not my population proportion, right? And so then what we do is we say, then I feel that I have enough evidence to reject the null hypothesis. I want to emphasize, this is a quick and dirty approach for hypothesis testing. It doesn't tell us the likelihood of certain outcomes under the null hypothesis, which we're going to get to, which is called the p-value. Okay? But it is a way to test hypotheses. And it is kind of the direction that the field is moving in, because we like to keep it vague. So to test the hypotheses, because I feel like I talked a lot, but I didn't write a lot here. The hypotheses H naught that P is equal to 0.50 and HA that P is greater than 0.50. A couple of things. Notice that there is no overlap, right? It either is 0.5 or it's greater than 0.5. Also notice that these two things are the same and these two things are the same, right? And so I can't change it up halfway through my hypotheses, halfway through my testing, right? And so really the only change is here. And for us in this course, I like to keep it nice and simple. Of course, if you have a greater than here, you could say that P is less than or equal to 0.5 here, but I find that that's a lot to keep track of. So for me, I'm fine with just always having an equal sign in your null hypothesis. And so we always have an equal sign in H naught. I didn't make it very long today. Sorry, need to sit down. Yeah, or water or something. Or hypothesis testing just taking it out of me. I don't know. Else. In fact, I should, now that I can look at this clearly here, I'm going to use just a different color here so I can talk about each of these. Okay. So notice that your hypotheses, let's start here. So you have your null hypothesis and your alternative hypothesis. Right? These are statements, right? And so that's why you have to use the colons and not equal signs, right? And so here, these, what color haven't I used? These are statements. Statements? All right, try again. These are statements. Okay. They have to be statements about the population parameter or just the parameter, right? In this case, it has to be about P. So it's a statement and it must be about the parameter. And we said, okay, we always have an equal sign in the null hypothesis, and then the sign in the alternative hypothesis is just from the question, right? And so it's determined by the question. So here the sign, oops, I'll move this down here. Sign is determined by the question. We've got some options. We could have not equal to, right? Is there a difference? You could have less than, or you can have greater than. Notice that there's no overlap with equal to, because the equal to has to be in your null hypothesis. And I'll snake this down here. And then the 0.5, they have to be the same for both hypotheses, right? And so these must be the same. I would say reading a question and setting up your null and alternative hypotheses is going to be one of the hardest parts. But with practice, right, then you'll start to kind of, oh, I know how to set this one up. I've seen something like this before, right? And so for now, we're just working with one sample proportion type questions, right? And so, so they will all look something like this. One sample proportions I'm hypothesizing about P, right? And how it relates to some number from the question. In this case, we want to talk about a majority, and so that's where we get the 0.5 from. On your formula sheet, where's it? Once you've decided that you have one sample proportion as your type of question, now we've only seen that one type of question, and so that's nice for now. But once you figured out that you need to do a hypothesis test for P later, notice that I even give you the general form of the null hypothesis. And so here I give you what the null hypothesis should look like. H naught, or the null hypothesis, is that P is equal to some number P naught. Now this P naught is just a placeholder, right? It depends on what the question is asking you, right? Is there a majority, right? Then P naught would be 0.5. Is it less than 30%, right? Then it would be 0.3. And then your alternative would be P is less than 0.3, right? So here, P naught is a placeholder for a proportion from the question. Why don't I give you the alternative hypothesis? Because by giving you the null hypothesis, or the general form of the null hypothesis, right? Then, well, if the alternative has to be about P, right? And it has to be about P naught in general. And then the sign for the alternative hypothesis depends on the question again, right? Do you want to know if it's more than 0.5, maybe less than 0.3, different from 0.7, right? So we'll see all those, but just kind of keep all that in your head for now. I know, it's a lot. Okay. So we found, so last day, we found the 95% confidence interval, and I'm just going to use the proportion 0.64 to 0.67, just from earlier. Now, remember the interpretation? We didn't get to do very many, so we use that same standard interpretation for the confidence interval always. Now, you don't need to interpret it here, but I think it's going to help us figure out whether we can reject H naught or not. And so we are 95% confident in this case. The interval from 0.64 to 0.67, rounding pretty heavily, but that's okay. Captures, right? We wanted to have that word captures because the population proportion is fixed and we don't know where it is, right? So captures the population proportion of American Facebook users, blah, 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 who think Facebook categorizes their interests accurately. Who think Facebook categorizes their interests accurately. If we're 95% confident that P is somewhere in this range, right? Then what we can do is we can say, okay, well, on a number line, which is always nice, P is between 0 and 1. Right? Always. And so 0.5 would be in the middle here. And we said, well, I'm 95% confident that it's somewhere between 0.64 and 0.67. So here, 95% CI for P. Our null hypothesis was that P is 0.5. So here, H naught says that P is equal to 0.5. But that's outside my 95% confidence interval. And I'm really confident 95% is quite high, right? And so I'm 95% confident that P is actually somewhere in here. Now we saw those scenarios where, okay, maybe we have a bad sample, right? And so 5% of the time we're saying, hey, I could be wrong, right? I could have a weird sample here, but the 95%'s got to count for something, right? And so then we say, okay, well, I'm 95% confident that it's between 0.64 and 0.67, which is also saying I'm 95% confident that P is not 0.5, right? I'm not 100% confident. I'm only 95% confident. And that's what bugs a lot of people about statisticians is we'll never commit to anything. Oh, there's still a chance that we're wrong. That's okay, right? But here, so therefore, we are 95% confident P is above 0.5. Which gives me evidence against H naught, right? H naught was saying, hey, P is 0.5, don't worry about it. And then we said, well, that's not what my numbers are telling me. My data is telling me that it's somewhere between 0.64 and 0.67, right? What do you have to say for yourself? Well, you could be wrong. No, it's not that much back and forth, but so we're 95% confident that P is above 0.5. Which means we have evidence against H naught, right? Because the null value is not in the interval, right? If our interval was somewhere between, 0.4 and let's say 0.6 by symmetry, then yeah, I would say I would feel comfortable just concluding that, okay, P is 0.5, that seems reasonable, right? As long as it's somewhere in my interval, I'm okay with that. Okay? But in this case, it's not, so I'll erase this, but. Which means we have evidence against H naught in favor of HA. Right? It looks like the alternative hypothesis might be true where P is higher than 0.5. Notice how we're not committing to a number, right? We would have to do another hypothesis test to do that, but we are okay saying, hey, I am comfortable saying that P looks like it's greater than 0.5, right? Just based off of this interval. And so therefore, another therefore, I guess, put this down here. No. which means we have it in favor of HA. We conclude a majority of can I just copy and paste because I'm lazy? Majority of American Facebook users. Did it save me time? I don't know. Who think Facebook categorizes, also trying to keep it on one page. Wait. Categorizes their interests accurately. I guess I wasn't ready to leave a page yet. So to test a hypothesis, right, some idea, using a confidence interval, we follow these steps. To test a hypothesis using a confidence interval, step one, from the question, you're going to state your null and alternative hypotheses. State H naught and HA. In step two, you're going to calculate the confidence interval, right? Usually the default is a 95% confidence interval. Calculate the confidence interval, I'll abbreviate CI, and usually 95% is the default. So you want to calculate the confidence interval, and then what you want to do is see if the null value is inside the interval, or if it's outside the interval, then that's evidence against H naught. So compare the null value to the confidence interval. So there's two options. Option one is that you have a number line like this, 0 to 1. And in the interval that you found, right, so here's your 95% confidence interval. And somewhere in here, and it doesn't, I want to emphasize that it doesn't have to be in the center, right? It can just be anywhere in the interval. H naught says that P is equal to some generic P naught being a number. But P naught is somewhere in this interval, right? Then I'm 95% confident that P is P naught. Fine. I don't have enough evidence to reject H naught. So if the null value, which is P is equal to P naught, is in the interval, we do not have enough evidence to reject H naught. We do not have enough evidence to reject H naught. Notice the funny wording there. Again, it's because I only built a 95% confidence interval. I recognize that there's a 5% chance that I'm wrong, right? And so that's why we have to be really careful with how we phrase this, right? And so we have to say we do not have enough evidence to reject H naught. Why are we talking about H naught? Because we did all our testing assuming H naught was true. And now I'm finding, hey, it's a reasonable result, right? Option 2 is what we saw. Option 2 is if we build our interval, so our P is between 0 and 1, and again, we build a 95% confidence interval here, and maybe my H naught is that P is equal to P naught was way down here. It's outside the interval, which we found. Then we would say, okay, if the null value, which again is that P is equal to P naught, is outside the interval, or is not in the interval, I should say, not in the interval. You'll see why in a sec. So is not in the interval, then, so if it is in the interval, we do not have enough evidence. So if it's not in the interval, then we do have enough evidence to reject H naught. I'm 95% confident that this is not an option. Right? And so then, if the null value is not in the interval, we have enough evidence to reject H naught. And if we reject H naught, usually we say in favor of HA. So notice we only have two options, right? We do not have enough evidence to reject H naught, or we have enough evidence to reject H naught. Those are your only two conclusions. These are the only two possible conclusions. Give myself. And notice that the conclusions are in terms of H naught, right? And we'll see that more clearly later on, but that's because we did everything assuming H naught was true. And so notice conclusions must be about H naught. That's really important. And I'll say since we do our testing assuming H naught is true. For the confidence interval, we didn't have to assume a P. In fact, we assume that P is P hat for a confidence interval, and that's okay, right? Because we don't have any idea for P. But later in hypothesis testing, in kind of true hypothesis testing, we calculate a test statistic instead of a confidence interval. Okay, but just remember these things because I had a hint that we're going to talk about decision errors. So if we're using a 95% confidence interval, for example, right, then I've already acknowledged probably 2 or 3 times that, hey, there is a 5% chance that I'm wrong, right? That this interval doesn't represent the population and we're making a bad decision, right? And so if our conclusion in either of these scenarios, whichever way we decide, is wrong, the problem is we don't know if we're wrong. We'll never know, right? But we do have to recognize that there are decision errors that I could be making. And so depending on what our conclusion is, depending on our conclusion, which is either reject H naught in shorthand, right? You either have enough evidence to reject H naught, or usually we say fail to reject H naught or FTR in shorthand. Right? There is not enough evidence to reject H naught. Notice how I'm working very hard to not use the word accept, right? Because accepting ignores that 5% chance that I'm wrong, right? And so you want to be really, really careful that you never accept a hypothesis, okay? Because we could be wrong. And so depending on our conclusion, we either reject H naught or fail to reject H naught, there is a chance, right? 5% chance or probability for a 95% confidence interval, for example, right? But in general, there's a chance that our decision is wrong. Our conclusion or our decision is wrong. Now here, this is why we never, I'm going to do capital never. This is in red. That's important. This is why we never accept a hypothesis. I will take marks off if you tell me that you accept a hypothesis, because like I said, it ignores that 5% chance, which we need to recognize, right? That I could be wrong. I have I'm basing everything off of a sample, and despite my best efforts, the sample could just be a weird sample, right? And so we always have to recognize that. I'll even write it here. This is why we never accept a hypothesis, and I will take marks off if you say accept. I really hope that this isn't one of those scenarios where, oh, there was something about accepting, and then you write accept. Don't do that. Go the opposite way. At Tim Hortons, I get a steep tea with 2 cream, no sugar. And so when I first started dating my husband, when he would order, he would always say, oh, could I get a steep tea with no sugar and 2 cream? And I was like, no, you said sugar. So hopefully this isn't what's happening here. And then sure enough, there will always be sugar. So anyways, you say it and then, yes, but don't say accept. Yeah. And today, sugar, I'll have none. So I will take marks off, but you've been warned. It's even in the notes. Not bad. So what are these decision errors? There are only 2 errors that I could make, right? I either say I do not have enough evidence to reject H naught. If I'm wrong here, what should I have done? I should have rejected H naught, right? Or if I say I have enough evidence to reject H naught, then if I'm wrong, then I shouldn't have rejected H naught, right? And so those are only two scenarios. The problem, or kind of the conceptual problem, is that we don't know what the truth is, right? And so we can talk about decision errors and just use it as a tool. Usually we say, oh, but the probability of making a type 1 error, so we have a type 1 error and a type 2 error, is this, right? Anyways, it's here on the next slide, so I'm getting there. But for example, so hypothesis tests are not flawless, right? We've already recognized that, hey, there's a chance that I'm wrong, right? And so, for example, in the court system, and they love using the court system, right? You're in court and you're convicted or you're not, but innocent people are sometimes wrongly convicted and then guilty sometimes walk free. And so those would be decision errors, right? You found evidence that someone should be convicted when they shouldn't, right? Or you didn't find evidence that they should be convicted when you should have, right? And so now, right, the difference is that we'll have kind of a way of quantifying these errors. So we have two competing hypotheses, right? The null and alternative hypothesis. Now, we have our decision that we've made, right? So here, up here, we have the decision that we made. We either fail to reject H naught or we reject H naught, and those were only two options, right? Now, there's some truth that, and we don't know, we will never know the truth, right? So that's a tricky part, but that's why we're doing statistics in the first place, right? If we could know what the truth is, then we don't need statistics. If the truth is that the null hypothesis is true and you decided, hey, I don't have enough evidence to reject H naught, then that's a good decision, right? That was the right decision. If H naught is true and you say, hey, I found evidence against H naught, right? Then you're in that 5% kind of off sample. We call that a type 1 error. And so what I want to clarify here is if we reject H naught, there's always a chance that we're making a type 1 error, right? A type 1 error, if I rejected H naught, would be I've rejected H naught when I shouldn't have. Okay? And so if we reject H naught, there is always a chance we are making a type 1 error. So if you fail to reject H naught, you can't make a type 1 error. You can make a type 2 error. Type 2 error, slightly different, is when you don't find evidence against H naught, so you fail to reject it, when you should have rejected it. And so usually we focus on the type 1 error. And so again, if you fail to reject H naught, then there's always a chance that you're making a type 2 error. So if we fail to reject H naught, we could be making a type 2 error. So it's just good practice to recognize that you could be making these mistakes and you don't know, right? And so kind of recognize the flaws of your data, your study. Now, let's see here. Okay, I'll try my best to save it. Can I do it? I'll hold it in. Okay, I can do it. Like I said, we almost never know which one is true, the null hypothesis or the alternative, right? But we need to consider all the possibilities. But as long as you remember, okay, if I reject H naught, then I could be making a type 1 error. And then you remember, okay, then the opposite must be a type 2 error, right? And so you really only need to remember the one, right? And then you've got the other one kind of baked in, right? The opposite. And remember, there's only two types of errors. Right? Or my favorite multiple choice question is a type 1, a type 2, or a type 3 error. People do choose type 3 error, but then I don't feel bad not giving them any marks. So if we think about our hypotheses or a hypothesis test as a trial, now I'll admit when I was learning this stuff, I didn't find that this was very helpful. So I'll introduce it in case it's helpful for you, but if not, then just focus on kind of what the errors are, right? And recognizing that there's always some probability of making a mistake. Okay. So what we can do is we can talk about our null hypothesis as, okay, the defendant is innocent, right? Innocent until proven guilty, right? And that's the case for all our null hypotheses, right? We had to assume that P was 0.5 until I had a confidence interval that told me otherwise, right? And so this is the same as kind of having an equal sign in your null hypothesis, right? Is, okay, nothing happened here, this person's innocent. Okay. Once I have enough evidence against that, though, then I can conclude that the defendant is guilty. Okay. So which type of error is being committed in the following circumstances? Declaring the defendant innocent, okay, that would be the same as failing to reject H naught, right? If you say, hey, this person's innocent, right? That's the same thing as just kind of keeping H naught. Okay? And so here, this is fail to reject H naught when they're actually guilty, when HA is true. That's a type 2 error, right? If I fail to reject H naught when HA is true, that's a type 2 error. So it's a type 2 error. Oops. Versus declaring the defendant guilty, okay, that would be equivalent to rejecting H naught. So reject H naught when H naught is true. Whenever you reject H naught, there's always a chance that you're making a type 1 error, right? And so here, it's a type 1 error. And then I think I have. There is this argument, and maybe this is, it's hard when we're talking about kind of, innocent and guilty, but which error do you think is the worst error to make? Right? And so in this case, right, we've got a quote to kind of lead us down the path, but better that 10 guilty persons escape than that one innocent suffer. And so the idea is, okay, well, declaring someone guilty when they're actually innocent is worse than saying, okay, yeah, you're innocent when they're actually guilty, right? And so here, by this, a type 1 error would be considered worse. Okay? Saying that there is evidence of something when there isn't, right? Then that is generally considered worse. Oops. There. Okay. We've seen the term p-value, but briefly, should have introduced it. But what we're going to use in formal hypothesis tests, we're going to find some p-value. Okay? Now, the probability or the p-value is a probability. Okay? And so I'm going to add it in here. Add a page. Yeah. In formal hypothesis testing, we will find a p-value. We will find a p-value. So let's see, what is the p-value? The p-value, it is a probability. In fact, it's the probability of seeing an observation as extreme or more extreme than what we saw. The probability of seeing an observation, or if you prefer, an observation or statistic as extreme or more extreme as what we saw in our sample, assuming H naught is true. Okay. Let's briefly for a moment here assume conditions for inference are satisfied. They're going to be very similar to what we had for a confidence interval, but just with a minor twist. But let's just assume that they're satisfied. What does that mean? It means that we can use, oops, oh my pen. We can use the fact that p hat follows a normal distribution centered on p with a standard error of PQ over N square rooted. Right? Now from here, what the normal distribution says, okay, we have a normal distribution, then remember a probability, if we have a normal distribution, a probability is an area under the curve. Right? And so what we're going to have is we want to find some area under the curve, right? A probability of seeing an observation or a statistic as extreme or more extreme as what we saw in our sample. Okay? Assuming H naught is true, which means that, okay, if H naught is true, H naught says that P, the center of the normal distribution, is at P naught. Okay? We assume that's true until we find evidence against it. Okay? Then, now, I have maybe some P hat, some sample proportion that I found from my sample. P hat somewhere on the upper end. Okay. Now, what I want, because this is now a scale of proportions, right? Centered on P naught, and I found my sample proportion is above P naught, right? But we need to know if it's significantly above P naught. Okay? And so at some point here, we're going to say, hey, this P hat is really far away from this P naught. It's very unlikely that it came from a distribution centered on P naught. So what we do then is we say, okay, well then this area here, the probability of an observation as extreme or more extreme, that puts me in the tails, right? And so our p-value is always going to be the area in the tail. Z. This is what we call a one-sided p-value. Because it's just one of the tails, right? Or a one-tailed p-value, one-sided or one-tailed p-value. Okay, but for now, let's just focus on the p-value itself. Okay? So it's going to be the probability of something as extreme or more extreme, which puts you all the way into the tail. And we know how to find these areas, right? We can calculate a Z, which we can, right? Then we'll be able to find this area, right? So then, assuming that P is equal to P naught. So how we draw our conclusions is we say, well, if the p-value is small enough, then we have enough evidence to reject H naught. And so usually how I think about it is there's kind of an invisible region here where, let's say like this, where we would fail to reject H naught. There's kind of some wiggle room for if I find my p-hats are somewhere in this range, that's okay. That's basically the same as P being P naught. Because I know my samples move around, right? And so it's kind of like, am I sitting at the desk? Yeah, right? I am sitting at I'm not sitting like this at the desk, but I'm allowed to sit like this and still be considered I'm sitting at the desk. I'm sitting at the desk here. Oh, where's Emily? Oh, she's over there sitting at the desk. Even here. And then at some point, you would, I'll scoot back here. You would say, oh, she's over there by the whiteboard. right? Because I've moved so far away from the desk that you don't feel comfortable saying, hey, she's over there sitting at the desk. Where is she? Yeah, kind of a weird scenario, but right? And so then you would say, oh, she's over there by the whiteboard, right? Which would be the same as rejecting the null hypothesis that I'm sitting here at the desk. But I'm allowed to be, there's some wiggle room, right? And so same thing for us, there's some wiggle room, right? All of these values, we would say, yeah, P is basically P naught. I can't argue with that, right? I'm happy with that. But then at some point, we need that stopping point, right? We need some way of saying, nope, because the p-value is so small, right? Then I can reject H naught, okay? So what we're gonna find is that if the p-value is small enough, everyone loves that, small enough, right? Really what I mean is less than the significance level, which we denote by alpha. So a new Greek letter, alpha. Alpha is the fish. And so alpha so if it's less than the significance level, alpha, where the default alpha level, default alpha is 0.05. And that is linked to our default 95% confidence interval, right? For example, if my confidence interval is this guy here, right? 95% confident, then I have 5% split between the tails, right? And so that default alpha level is directly related to the confidence level, or the significance level, I should say. Nope, I meant confidence level for our confidence interval. Okay. But if the p-value is small enough, right, what that means is that p hat has moved far enough away from p naught for us to say, okay, I did everything assuming that this was my center, but now I'm finding that that's unlikely. It's possible, right? There's a p-value probability of it happening, okay? And so then, but we say, hey, because it's less than the alpha level, 0.05, so 5%, yeah, then we have enough evidence to reject H naught. And so if the p-value is small enough, so less than the alpha level, we have enough evidence to reject H naught in favor of HA. And on the flip side, right, if the p-value that we find is not less than the alpha level, right, then we do not have enough evidence to reject H naught because it's close enough, right? And so versus if the p-value is not less than the alpha level, right? The default is 0.05, okay, but any alpha level, If the p-value is not less than the alpha level, we do not have enough evidence to reject H naught. If you compare these two sentences, one is just the negated version of the first one, right? Or the second one is just the negated version. So if the p-value is less than the alpha level, then we have enough evidence to reject H naught. Yeah. And if you're rejecting it, you should say in favor of what, but just you can stop there if you want. Versus if the p-value is not less than the alpha level, then we do not have enough evidence to reject H naught. And again, those are your only two sentence structures that we can use. So it either is less than the alpha level, which means we do have enough evidence to reject H naught, or it's not, and we don't have enough evidence to reject H naught. So we still don't know how to find that p-value, although I think if I gave you enough time, you can figure it out, right? But I won't make you do that. But I did have to talk about what the p-value is, because here we talk about it, okay? Coming back to our type 1 error rate. So as a general rule, we reject H naught when the p-value is less than 0.05, okay? Or we use a significance level of 0.05, or alpha is 0.05. Like I said, that's our default. A lot of questions will say use an alpha level of 0.1 or use an alpha level of 0.01, right? So that'll just determine what your cutoff is. This means that for the cases where H naught is actually true, right? We're saying, well, we don't want to incorrectly reject it more than 5% of those times. I'm rejecting it, but there's a chance that I shouldn't. Maybe we just have a weird sample. And so really what we're saying is when we use a 5% significance level, or we're going to shorthand this, when we use alpha equal to 0.05, really what we're saying is that there's about a 5% chance of making a type 1 error. In fact, I'm declaring before I even start my study, right? You pick a significance level. You would say, I'm okay making a type 1 error, 5% there's a 5% chance. Now, if it's really expensive to make a type 1 error, right? Rejecting H naught when you shouldn't have. For example, saying we need to tear this whole building down and build a new one when you don't actually have to. That's expensive, financially expensive, right? Then you would want to be really, really sure, which means that you would decrease your alpha level, right? And so that's when you would use a 0.01 or, right, a 1% chance of making a type 1 error. And so there's about a 5% chance of making a type 1 error if the null hypothesis is true. This is a conditional probability, right? The probability of making a type 1 error, given that H naught is true, is the alpha level. Okay. And so here, I'll add a note. So we prefer small values of alpha. Increasing alpha increases the type 1 error rate. And if making a type 1 error is expensive, usually we're talking about financially expensive, but maybe in terms of what it makes people do. There's a Tylenol debacle, for example, and if the repercussions are expensive, right, to society, right, then you want to be really, really sure before you go out and publish a study, So then you reduce your type 1 error rate, which is your alpha level. Now, I haven't looked at what, I don't even know if it was a real study though, but I should look more into it. But if making type 1 error is expensive, we use a small alpha such as alpha is 0.01 or 0.001 if you want to be really, really sure. But the problem is then rejecting H naught becomes really difficult because then you'd need a really, really large sample size. I'm going to add just a quick note here. The one that I was kind of thinking about earlier, but we usually can't control the type 2 error rate, which is why we're focusing on the type 1 error rate. That's our alpha level, right? We have control over that. A type 2 error rate. Remember, a type 2 error is when I fail to reject H naught when I should have rejected H naught. All that's really saying is that my sample didn't give me enough evidence to reject H naught. Usually the main problem there is my sample wasn't big enough, right? I wasn't able to detect something with clarity because if I have a small sample size, then I have a lot of spread, right? And so then I'm kind of unsure of my results. And so we usually can't control the type 2 error rate. As it is usually linked to small sample sizes. Once you've collected your study, there's a reason you collected that sample size. Maybe you are not able to get a larger sample size, right? And so a type 2 error, we can't really control it. But if you wanted to, you could increase your sample size, right? But there's a reason you haven't. So I just wanted to make a note because we talk a lot about the type 1 errors because we can control them, right? Okay. Let's see here. I do want to do this. Why? We are going to do it. And we're going to do it together. But let me just... Fine. I was saving it for later. If the P is low, then the null hypothesis must go. Just rolls off your tongue. Keep that there. Inappropriate, yes, I'll admit that. But helpful, also, yes. And usually on final exams, I'll see it kind of scribbled on the front page or something because it is catchy. And this idea, okay, I'll bring it up here. Copy. I had to see how much I'd forgotten to do here. I'll put it here, but I'll make it smaller. So here, if the p-value is low, so if the p-value is small enough, then you have enough evidence to reject H naught, is really what it's saying in a quick and inappropriate way. But it is helpful. So I keep it in there. So that is to summarize this, but also remembering one of the options, then you also know the other option, right? You just negate it. Right? I'll say here, what this is really saying is if the p-value is small enough, right, less than the alpha level, then we have enough evidence to reject H naught. Like a lot of things in this course. Even if this doesn't make sense, having something that helps you kind of memorize it in a way is going to be super helpful until it all starts falling into place, right? But I guess what I'm asking of you is patience, right? So just kind of take it all and don't expect it to make sense at all. I don't expect it to make sense for another couple of weeks at least, okay? And so don't worry, right? But we'll kind of piece things together as we go. Okay? And whatever you need to do to memorize it in the meantime, do it. Okay? The conditions for inference for a hypothesis test. I said earlier, hey, let's just assume that the conditions are satisfied, right? The conditions for inference are what allows us to use a normal distribution, right? And so it's important that we check them. Now, for hypothesis test, it's going to be slightly different than a confidence interval, right? It's going to be very similar, but right, similar to testing for a confidence interval, right? Except the normality condition. So the independence condition is the same. If I have a random sample, then I can assume independence, right? We can assume independence. I'm gonna say that this one is optional. The n less than 10% condition. Remember what that one is? Because I just finished talking about, okay, increase your sample size, right? But not too much, not more than 10% of the population, because then you're introducing non-independent observations likely. But it's optional because I think it's kind of overkill. But n must be less than 10% of the population. Usually that's not a problem. Right? We can't afford to take 10% of the population. Now, the normality condition is the slight change. Do you remember what it was? So recall for a confidence interval, the normality conditions were these. I need at least 10 observed successes and I need at least 10 observed failures. At least 10 observed successes. So you can find X is the number of successes, or if you have N and P hat, those will be the same number. They have to be greater than or equal to 10. And we need at least 10 observed failures, which is N minus X if you have those numbers, But you could also have n times q hat if all you are given is the p hat, then you can use q hat for the number of failures. Huh? Now, for a hypothesis test, we need at least 10 expected successes. So it'll look very similar. But how do we find the expected successes? Well, the expected successes, assuming H naught is true. Okay. And so from your null hypothesis, you'll have that P is equal to P naught. And I'll move this down the line. And so your expected successes under the null hypothesis would be n times P naught. Has to be greater than or equal to 10. So the expected successes versus the observed successes. And the expectation comes from the null hypothesis. And I think you can guess it. You need at least 10 expected failures. N times Q naught has to be greater than or equal to 10. Where, of course, Q naught must be 1 minus P naught. All right, we've seen this PQ relationship, right? P and Q, Q is 1 minus P, P at Q hat is 1 minus P hat, right? And so it makes sense that Q naught would be 1 minus P naught, of course. And so again, you've got your observed successes and failures for your confidence intervals, right? Or if you read the question and you see that, okay, I'm going to do a hypothesis test, then you need to check that you have at least 10 expected successes and failures. If you read a question and you see that you have to do a confidence interval and a hypothesis test, well, guess what? Then you need to check all of them. Right? Again, they're all going to pass, right? They're all going to be satisfied, but we have to know how to check the conditions. Okay. Now I think we're ready to do an example. In fact, I'm just going to continue on this page. I am going to use this example to also outline what we would need to do for the steps of a hypothesis test in general. Okay. So we're talking about the same survey, and it asked 850 respondents how comfortable they are with Facebook creating a list of categories for them. And 41% of the respondents said that they are comfortable. Now, if it's 41% of the respondents, that's a sample proportion. Right? Do these data provide convincing evidence? Now, again, we've seen this, or I highlighted it before, but this is a clue that I have to do a full hypothesis test. That the proportion of American Facebook users I think who are comfortable with Facebook creating a list of interest categories for them is different than 50%. And so what we have is we have some p hat, our sample proportion is 0.41, but the number that we want to compare that to, or the proportion we want to compare that to, is 0.5. Right? So that tells me that my p naught must be 0.5. In terms of the steps, and I need more room here, but I'm going to call it step 0, checking the conditions. Not very helpful, I know, but it's because all my solutions, I usually do it separately and then step 1, 2, 3, 4. And so I'll start with step 0, check the conditions. Reading this question, I only have to do a hypothesis test, right? And so I need to make sure that the independence condition is satisfied and that I have at least 10 expected successes and at least 10 expected failures. Okay. And so for the independence, it doesn't say in this blurb that they were randomly selected. And so then what do? We say we assume the sample was randomly selected, right? We assume the sample was randomly selected. Which is why sometimes I call it check the assumptions instead of check the conditions. And so I'll add that here, conditions / assumptions. Right. Sometimes we just state what we're assuming in order to proceed. The optional one, n less than 10%, right? We said 850 is less than 10% of American Facebook users. So that's the independence section. Now, how about the normality part? Since I'm only doing a hypothesis test, like I said, I only need to check the expected successes and the expected failures. And so we need at least 10 expected successes. Now that's the expectation at the 50% or at p equals 0.5. Okay. And so n times p naught is 850 times 0.5, which is 425, which is greater than or equal to 10. Doing the same thing for the expected failures. Of course, if I'm splitting it in half, right, then they should both work. At least 10 expected failures. N times Q naught is 850 times 1 minus 0.5, which is still 425, which is greater than or equal to 10. And that's good. Now we can move on with our lives and do the hypothesis test. Right? Sometimes I like to say, therefore, the conditions for inference are satisfied. On the tests and on the final exam, there will be questions where you have to check the conditions, right? I have to make sure that you know how to do it. Okay. Sometimes, or more often, I'll say, you may assume the conditions for inference are satisfied. And then you can skip this step, right? So most of the time it'll just say, hey, you can assume the conditions are satisfied, move on. And jump into step one. Step one of your hypothesis test is always going to be to state your null and alternative hypotheses, or state the hypotheses. Even if you don't know where to start at all, right? How about starting here with a null hypothesis with a colon, followed by an HA with a colon. Great place to start, right? And now we need to fill these in. Now, our null hypothesis, remember, always has an equal sign, right? And so let's jot that down. Why not? And I have a sample proportion, right? And in this question, when I read it, I have one sample of 850 respondents, and I have one sample proportion from this sample, right? Telling me that this is a one sample proportion type of question, right? And as we grow, right, we'll introduce different types of questions, right? And so, but for now, we only have the one sample proportion. If you look at your formula sheet, under one sample proportion type questions, right? I've given you the bare bones of the null hypothesis, right? It tells us, hey, our hypothesis test has to be about P. We've learned that already. It has to be about the population, right? And how P relates to some P naught. Huh? P has to stay P. Oops, P. And P naught is the number we want to compare our sample proportion to, right? Which from the question, and it'll always be from the question, is 0.5, right? Is it different than 50% or 0.5? So P is 0.5 because P naught is equal to 0.5 is from the question. It's the value we want to compare our P hat to. It is the value we want to compare P hat to. Now from here, we said, okay, well, if I'm talking about P in my null hypothesis, then I have to talk about P in my alternative hypothesis as well. So we're getting there. And if I'm talking about 0.5 in my null hypothesis, then I have to talk about how P relates to 0.5 in a different way in my alternative hypothesis. So now the only thing that's going to be different between these two is the sign here. Now, that's going to depend on the question. Now here is different than 50%. What that's going to tell us is, well, if it's different, then P is not equal to 0.5. Right? And so that's how we get our alternative hypothesis not equal to. Okay. The sign depends on the question. Not equal to is if there's a difference. Less than, of course, is less than. And greater than is, of course, greater than. Or some version of those. But in this case, we want the not equal to because we want to know, hey, is it just different from 0.5? And we don't care which direction it's going in. So when we're talking about a difference, then we call this a two-sided test. I don't care which tail it's heading into, the lower tail or the upper tail. It'll be in one of the tails, right? But I don't care which one. Whereas these two are called one-sided tests because I only care about one extreme. I highlight that here because we'll need that when we find the area under the curve later, right? Which area am I interested in? But for now, we've established our null and alternative hypotheses. How about the next step? Step 2, we haven't seen yet. This is technically where we're going to calculate the test statistic, which is hard to say. But we're going to calculate the test statistic. I often call it do the test. Do the test, do the do. Because it's quicker than saying calculate the test statistic. But, okay, test statistic. Don't really know what that is. If you had to kind of take a stab at it, knowing that we need to eventually find an area under the curve, then maybe calculating a z is a good place to start, right? And so that's on your formula sheet. I'll grab it here. So if you're doing a hypothesis test, then for all the different question types, I give you step 1-ish, kind of a general version of step 1, state your hypotheses. And I also have to give you how to calculate the test statistic. Right. So here, this is step 1. And this is step 2, the test statistic. So do the test, in this case, for a one sample proportion, really means calculate Z. Right? Calculate Z. Uh-oh. Z is p hat minus p naught divided by p naught q naught over n square rooted. Notice how we've replaced our p hats and our p's with p naughts. And that's because we're assuming the null hypothesis is true, right? And so here, since we are assuming H naught, which says that P is equal to P naught, is true. Right? I know. Can we just calculate the Z? Can we do that? In this case, p hat was 0.41, right? Our sample proportion from our 850 respondents was 0.41. Really what we're seeing is how far is that from our hypothesized proportion of 0.5? P naught. Taking into the account the spread of 0.5 times 0.5 divided by 850. Oh. Can't do that in my head. 0.41 minus 0.5. Negative 0.09. And then 0.5 times 0.5 divided by 850 divided by the square root of 0.00029117647. But you have to take the square root. If you don't, you're going to get gigantic values of Z. So if you forget the square root, your Z's going to be huge, which can happen. But if it's happening consistently, better check your work. 0.01714985551. Negative 0.09 divided by that. I get a Z of negative 5.2478567005. Even without the formal framework, which will continue on Tuesday, what's your gut reaction? Well, if P is 0.5, then I just happen to find something 5.25 standard errors below the P. And that's rare, right? Very rare. So I suspect I'm going to reject H naught. I encourage you to try to find the probability or take a break for the weekend, and I'll see you on Tuesday. Yep.